We're going to start a new unit today. This will keep us busy for at least a couple of 2 or 3 lectures. Ideally, I would have liked to spend a good third of the semester on this topic, but the semester is only so long. We're going to talk about Bayesian learning. To kind of introduce this, I want to go back to this what feels like a central theme for the entire semester, which is what does it mean to learn? Different ways of answering the question gives us different ways to invent new learning outcomes. We've already encountered 2 different answers to that question. The first answer gave us mistake-driven learning. What we define as successful learning is when the classifier or the system stops making mistakes. Mistake-driven, mistake-bound learning counts the number of mistakes and tries to bound it and says if this can be bounded in a polynomial sense, then learning is successful. Then we looked at another way to answer the same question with pack learning. We defined learning as finding a good enough approximation of the true concept and doing so with high probability. And this line of thinking gave us ideas like sample complexity and such things. Under both models, we can invent different learning algorithms, and there are many different learning algorithms. In the online setting, we looked at the perceptron, the original perceptron algorithm, but there are numerous other online algorithms that exist in the literature. Under the batch setting with pack learnability, we looked at a couple of learning algorithms. We looked at AdaBoost, we looked at SVMs, and also more generally this idea of learning at loss minimization, which is coming from a which owes sort of intellectual lineage, if that's the right word, to these concepts. Now, in all of these cases, what we have seen is the algorithm produces a function that gives a label given a new example. So the learning algorithm gives a hypothesis. The hypothesis is just a function. What can that function do? That function can label new examples. Given new x's, it can give you new the predictions for it. What we are going to do next is to attempt to answer this question of what does it mean to learn in a different way, using a probabilistic point of view. And this gives us the idea of Bayesian learning. And we'll look at least a couple of different learning algorithms under this regime. We'll definitely see logistic regression. And I'm contemplating whether I should cut naive Bayes because I want to spend more time on other things. I'll keep you posted. You'll know one way or another within the next few weeks. Today's lecture, and probably spilling over to the next one, is going to cover a few different topics. First, we look at the idea of Bayesian learning. And then we look at 2 different types of learning goals that we have under this perspective. One of them is called maximum a posteriori criterion. In short, it's called MAP, M-A-P. And the other one is maximum likelihood criterion. Then I'll instantiate the maximum likelihood criterion for 2 examples with 2 specific probability distributions. And hopefully at the end, you might notice something familiar. Let's get started. Let's start with Bayesian learning. Before talking about the idea of Bayesian learning, I want to kind of say that when we talk about probabilistic learning, there tend to be 2 different notions of probabilistic learning. The first one is that you learn functions that produce probabilities. So rather than producing a label, given an example, the learned concept itself is something that produces a probability. So you can think of the goal of learning is to learn C that takes an example X and produces a distribution that's really a number between 0 and 1. And you can interpret that number as the probability that, let's say, the example X is positive. The standard tools of learning theory that we have seen so far can actually be used to analyze this setting. But the one that's more interesting, or at least the one that's most relevant for this unit, is Bayesian learning, where rather than talking about the hypothesis that we will predict, the process of learning itself is probabilistic. The process of learning itself uses a probabilistic criterion to decide which classifier is good or which classifiers plural are good. In this setting, the hypothesis could be a deterministic function, like a Boolean function. It could be a decision tree, it could be a linear classifier. It's the criterion for choosing which hypothesis to pick. That's the probabilistic one. And that's the one that we are going to spend most of our time on. Eventually, we will kind of combine both of these things because it turns out that with things like with models like logistic regression, it uses a probabilistic criterion to choose a probabilistic concept, which is kind of neat. We'll get there by Thursday next week. Let's talk about Bayesian learning. Our goal is to find the best classifier or the best hypothesis from some set H given a data set T. This is the same goal that we've always had. The only difference this time is how do we define the word best? In this case, we are going to define the word best by saying the best one is the most probable hypothesis. We'll get into some details of what most probable means. We need to know, to talk about the most probable hypothesis, we need some way of characterizing a probability distribution over the hypothesis space. Only then is the question of what is the most probable hypothesis even well formed. So we need some way of saying what is the probability that this hypothesis is the right one for every hypothesis in the hypothesis space. It turns out that we also need to know something about the relationship between the data and the hypotheses, and we'll kind of I'll elaborate on the second point as we go along. You might encounter, if you hang out in the kind of circles that I do, you might encounter people talking about being Bayesian, about this or that. Essentially, that means we are treating this or that as a probabilistic thing, and we are imposing a distribution over this or that, in this case, hypotheses or parameters or labels or predictions or anything, and we are employing the Bayes rule to kind of help us move things along. What I said in the last 30 seconds might seem like it was completely vague, so let's we'll spend some time going into the details of that. Whatever it is, we've not talked about it. Bayesian methods, they can be seen as giving multiple sorts of, they have very interesting and useful properties. The most obvious one is they provide practical learning algorithms. Just like the VC theory gave us practical learning algorithms, being Bayesian about learning also gives us practical learning algorithms. The Bayesian perspective gives a systematic approach for combining prior knowledge about hypotheses with evidence that's seen in data. For example, if you knew that among all the hypotheses that exist, certain hypotheses are more likely. You can encode that knowledge that you have or preference that you have in a transparent way into the learning process. As a result, we can see learning not just as being the result of being a purely data-driven process, but in some sense using data to disambiguate our preference, what we already believe the hypothesis should be. And this is a fantastic conceptual framework, not just for designing learning algorithms, but also for evaluating the quality of learning algorithms. And as a result, the Bayesian perspective also gives tools for analyzing learning. I've not told you what any of this is. I'm just telling you, and this is mostly like a teaser. In the beginning, we have the Bayes theorem. Right. So we have the Bayes theorem, which hopefully all of you have seen. So you have random variables x and y. It just says this is just shorthand for saying the probability that the random variable y takes some value, little y, given that you know that the random variable x assumes the value x, is simply the probability of seeing x given y times your prior belief that the random variable y takes the value y divided by p of x, probability of seeing this x. Hopefully you've all seen this before. I don't know, like a third grade or something where they introduce this stuff. Right. So this is a rather old idea. It goes back to a posthumous paper from someone called Thomas Bayes. In this, we have these little pieces. We care about the label y. In this, or I take it back. Y is not yet a label here. We care about the random variable y. Y could be a label, y could be a hypothesis. We care about what value it takes. P of y is our belief that the random variable y takes a certain value before having encountered any evidence of the form x. The probability of x given y is asking what's the likelihood of observing this particular x had your y been some value. It's called the likelihood term. What we care about is the posterior probability, the probability of observing y given that x is observed. The probability that y takes a certain value given that x is observed. Notice that you have two probabilities, two distributions over the random variable y. The prior probability is a distribution that says, what's the probability that this random variable takes a value before having seen any data? The posterior probability is just saying what's the probability it takes the value after having seen some data. And the Bayes theorem says these two things are proportional to each other. And not proportional in any arbitrary way, but in a very specific way that is dictated by the likelihood. If we only care about the random variable y, then the usual sort of recipe for this is the posterior is proportional to likelihood times prior. We'll keep coming across this recipe again and again and again. The posterior probability is proportional to the likelihood of the data times the prior of whatever random variable that you observe, that you care about. Sorry. Questions about the Bayes rule? Yes. Good question. So let me repeat the question for Zoom. The prior is asking before you see any data, what's the probability of y? But how could you possibly have a probability of y before you see any data? Let me ask you a question in exchange. Have you checked the weather report in Antarctica today? You haven't. Do you have any belief on whether it's cold or hot? I've seen information about, but you haven't seen anything for today. Yes. So let's say the random variable. I'm just clarifying. Who knows? Maybe you are one of those people who follows Antarctica weather every day. Let's say the random variable here is it cold in Antarctica today? Today specifically. And your prior belief is most likely that it is cold. Right? Is that fair? But isn't that based on data? You have, but not about anything about today that you observe. So the random variable is asking about this particular day. You have inductively extrapolated from other information that you may have. We don't care about where the priors come from, because in this question today, X is simply the weather report for Antarctica today, and Y is it cold in Antarctica today? And you can think of the prior as before seeing the weather report, what's your belief in that random variable? And the posterior is after seeing the weather report, what should your probability be? And if you are mathematically correct in the way you have internal probabilities, these two things have to be proportional to this expression here, namely the likelihood. We are not talking about where the priors come from. In fact, that is an interesting philosophical question that we can take offline if you want, but there's like multiple answers to that. And it also has connections to what's the meaning of probability itself. But for now, let's kind of skip that conveniently because we only have, what, 3 weeks in the semester, and this will take longer than that. But yes, that's a very good question. Yeah.
The probability that X is your observation of X, but like, I don't know, I say it's a rock, but actually it's.
Oh, that is, you're introducing a new random variable. Then you introduce a new random variable and that you throw it into the mix. If you are Bayesian about, if you're truly Bayesian, and this is what I mean by being Bayesian, anytime you have this sort of question, what if this, what if that, what you have is a random variable. You start now, you throw that into the mix and you can now start reasoning about that also. The tool that kind of allows you to manipulate these objects around is the Bayes theorem. All of you have seen probabilities before, but maybe not today. So just a quick refresher. You have random variables. I'm using capital letters for random variables here. And there's a product rule. The product rule simply says, what's the probability of random variable A and or event A and event B occurring? I just write that as A comma B. And that's simply the probability of A given that B occurs times the probability of B, which is also the, I mean, there's no reason, there's no obvious ordering between A and B. So I can also say it's the probability that B given A occurs. The probability of B occurs given that A is observed times the probability of A. The sum rule is the probability of A or B happening. It's simply probability of A plus probability of B minus probability of A and B. There's this notion of independence. We have touched upon independence many, many times in this class so far, with data points being independent and all that. Whenever we say independent, we mean only one thing. Two events A and B are independent if the probability of A and B is simply the product of their individual probabilities. Alternatively, you can say, knowing that P of A and B is distinct, A given B times P of B is P of A times P of B. I can cancel these out, assuming that they're not zero. So the probability of A having observed B is exactly the same as probability of A having observed nothing. B does not influence A at all. So A and B are independent. So that's what I've written here. Probability of A given B is the same as probability of A. And you can do the same thing and say the probability of B given A is the same as probability of B. You should have seen this before. This usually shows up in the first 3 lectures of a probability class. Then there's a theorem of total probability. If you have mutually exclusive events, A1, A2, all the way through AN, which means that either A1 can happen, or A2 can happen, or A3 can happen, but not any pair of them. And with the total, the sum of their probabilities being equal to 1, which means the sum being 1 means exactly one of them has to happen, and 2 of them cannot. Then, for any other random variable P of B, I can say that P of B is the same, is equal to the sum over P of B given AI for each AI times P of AI. This is saying the probability of event B is, remember this is a sum rule here. Probability of event B is the probability of B given that A1 happened times probability of A1 plus the probability of B given that A2 happened times probability of A2 and so on. So B can happen when A1 happens, or when A2 happens, or when A3 happens, or even, and this is simply just saying that in a more compact form. Hopefully you've seen some version of this. This is just, I called it a refresher, but I haven't even given you enough time to read the slide. This is just for you to remember those concepts that you may have seen before and revisit them wherever you've seen it before, in case this doesn't seem familiar. Let's go back to machine learning. We are talking about Bayesian learning. Our goal is given a data set, we want to find the best hypothesis H. In the Bayesian perspective, we define the best using the notion of the posterior probability of the hypothesis given the data. The conditional probability of the hypothesis given the data is going to be used to define the best. The most probable hypothesis is the best one. But it's not just the unconditionally most probable, it's the one that is conditioned on having observed this particular data set you have. Given this data set, what's the probability of seeing classified? Let's kind of unroll this a little bit. We have probability of hypothesis given a data set. This is the posterior probability. It's asking what's the probability that H is a hypothesis given that the data set D that we are currently holding in our hands is the one that we was created by it. The important insight here is both H and D are treated as events. D is the event. I'm calling D the data set, but actually D is an event here. D is an event that among all the data sets that could exist, this particular data set is the one that nature decided to give us. H is the event that among all the hypotheses that could generate this data set, this particular hypothesis is the one that generated the data. In other words, this one is the true hypothesis. So both H and D are events, and that's the reason why I'm able to even put them inside a probability this way. The nice thing is now we can just blindly call upon Reverend Thomas Bayes to do his magic. So we can apply the Bayes rule. So we can the probability of H given D is simply the probability of D given H times the probability of H divided by probability of D. The probability of H, the prior probability, is saying it encodes background knowledge. It says, in the absence of any data, do we have any expectations about the hypothesis? Do we have any information that we can, any sort of preference that we can impose on the hypothesis space in the absence of any data? Notice that this also implicitly includes the case when we know nothing about the hypothesis space. Knowing nothing is saying that every hypothesis in the hypothesis space is likely, which means we have a uniform distribution. If we know nothing, if we have no prior knowledge, that is exactly the same as saying P of H is the uniform distribution. But we could have other preferences. We could say, for instance, using terminology from the previous unit, we could say that I would prefer simpler hypotheses somehow. In the absence of any data, I would prefer simpler hypotheses. If you can encode that as a probability, that becomes a prior. So we have these two terms. The posterior probability is the probability of observing, hypothesis being the correct one, the true one, having observed this data, and the prior probability is your background belief. Yes. You can think of it that way. You can map the prior to a regularizer and such things. You definitely can. And we will do that explicitly at some point. Yes.
So I think in this case, I can understand calculating the probability of states.
Yes.
But the probability of the distribution, isn't that depend on what like function is creating this distribution? Isn't that what kind of what we're trying to approximate?
Which one? Sorry.
Probability of D.
Oh, yes, the likelihood, right?
Yeah, the likelihood, yeah.
What's the probability that this particular data set or this particular example is observed?
Yeah, like we're trying to figure out what function is creating this data set. So how are we even?
But look at that expression there. It is P of D given H. When we are calculating the probability, we have a particular H at hand. We are given an H, we are given a hypothesis, and we are asking, what's the probability that this particular hypothesis created this data set? And I'll instantiate this a couple of times, and hopefully, by example, this becomes a little clearer. But at any point when you are computing that probability, you have the functional form of that hypothesis. And in fact, that is the first thing that you need to think about. what is the functional form of the hypothesis so that you can actually construct the likelihood.
Do we not hear about like just the probability of the third thing that's not highlighted?
The denominator, you mean?
Yes.
Good question. In practice, okay, so that's the next one. The denominator here, P of D, is just asking what's the probability that this data set is observed independent of any information about any hypothesis. Now, if our goal is to find the most probable hypothesis given a data set, we are going to try to maximize this quantity over H. This expression doesn't depend on H at all. As far as any H is concerned, 1 divided by P of D is a constant. So we are going to just discard it. In other words, we'll not even bother calculating. This goes back to the idea that P of H given D is proportional to the likelihood of the data given the hypothesis times the prior probability of the hypothesis itself. Questions about this? That is only if you're computing the max, which we will talk about next. But there are other things you could do. You could sample from that distribution. You could keep all of these in your hand and then do some sort of aggregation only at the prediction time or something in between. We're going to kind of talk about, in the interest of time, a particular class of these things, these ideas. I can see you're all eager for me to talk about something, one of these ideas. So let's talk about maximum a posteriori and maximum likelihood estimation. Our goal is to find a particular hypothesis. We need some criterion. The maximum a posteriori criterion or MAP criterion is simply saying find the hypothesis H, I'm calling it H map, that maximizes the posterior probability of the hypothesis given the data. The best classifier is the one that is the most likely given the data. But we already know that P of H given D it can be written in terms of the likelihood and the prior. So from here to here is exactly what we just saw. So P of H given D is nothing but P of D given H times P of H divided by P of D. We want to find among all classifiers the one that maximizes that quantity there. But notice, as I said before, this expression, the denominator, doesn't depend on H at all. So the function that the hypothesis that maximizes the thing in the box is going to be the same thing as the one that maximizes this expression here. I don't need to worry about P of D because it's a constant. So what we have here is just reusing the same thing that we saw before. The posterior probability is proportional to the likelihood times the prior. And finding the most probable hypothesis, finding the maximum a posteriori hypothesis, is identical to finding the hypothesis that maximizes the product of the likelihood and the prior. Yes.
So we don't actually care what the probability is so much as maximizing what the probability will be.
Finding the function, the hypothesis that maximizes the probability. Yeah.
Okay, so we don't care about the probability, we care about maximizing the
Yes.
function.
Yes.
And that's why we can ignore
The denominator. Yeah, that's right. That's exactly right. If we only care about the argmax, then we can just toss out the denominator. If you want a very simple way of thinking about it, let's say I have max over H of, let's say, let's not do H. Yeah, let's say my goal is to find the maximum value of X divided by 2. Well, the maximum value is 3 by 2. But let's say I don't care about and do you agree that the maximum value is 3 by 2? Okay. But let's say I don't care about the maximum value. I care about the argmax, the X that maximizes that thing. The X that maximizes it is actually 3. Right? Now, instead of that, if I remove the X divided by 2 and just get rid of a constant, the X that maximizes that expression is also 3. Because I'm just getting rid of a constant that does not involve X. Okay, so we have 5 minutes, and I think I should be able to do this part today. So our goal is to find, this is one criterion. This, with Bayesian learning, uh, we're going to encounter two different criteria for deciding which classifier is the best. So we already have one. The maximum a posteriori criterion is simply saying find the classifier that maximizes, or find the model that maximizes the product of the likelihood term and the prior term. There's a question on Zoom. Is P of H a function of the dimensionality of the hypothesis class? It could be a function of the dimensionality of the hypothesis class. Right now, we are not talking about that at all. We are just saying there is some prior distribution. In practice, we'll have to kind of come up with certain functions, and there are a few things that are studied in the literature. We'll see at least one of them, which are kind of natural priors for certain types of functions, and so they tend to be used because they make the resulting optimization kind of easy, and they are not terrible in that they don't impose unreasonable preferences. But for now, just pretend that it's a function of the hypothesis class, of the hypothesis. Yes. For the purposes of this class, let's say that we take the best one. In practice, you could take the top few. And then you get a committee that you kind of average over. You can construct an ensemble by sampling a few. That's a natural way to construct an ensemble. But the thing is, we may not always know we may not have any prior preferences. If I give you a data set, for example, and I say, what do you believe the classifier would be? You would be like, I don't know. Because you should probably have no preference. Having no preference over the hypothesis space is exactly the same as the case where the prior distribution is the uniform distribution. In other words, this quantity here is the same value no matter what the hypothesis is. And it's a constant, which means it can be pulled out of this argmax also. Doing that leaves us only with the likelihood term. And that gives us another criterion for Bayesian learning called the maximum likelihood estimation. The maximum likelihood estimation gives us a hypothesis that maximizes the value of the likelihood term alone. The likelihood, remember, is asking what's the probability that this particular data set was generated by this hypothesis. And you maximize that quantity over all the hypotheses you have, and that gives you the maximum likelihood estimator. The maximum likelihood estimator and the maximum a posteriori estimator are related to each other in that maximum likelihood estimation assumes that the prior distribution over the hypothesis space is uniform. In practice, we never maximize likelihoods and these products directly because they tend to be rather horrible looking expressions in the functional forms tend to be horrible. For some reason, all the distributions that tend to be used in practice, the log of the likelihood or the log of this product tends to be more kind of nice to work with, because we tend to work with distributions that are exponential forms. So in practice, we maximize the log likelihood, or sometimes some people write it as minimizing the negative log likelihood, which is the same thing. To kind of drive home the point that of what this maximum a posteriori estimator does, let's look at this one last thing for today that I'm calling the brute force map learn. It's a horrible idea, but it's kind of useful to just keep in mind because all other learners are going to do the same thing. We have a data set D and a hypothesis space H. Imagine that you have some magic ability to enumerate every single function in the hypothesis space, and this expression should be wrong. This is H. You enumerate every function in the hypothesis space, and you are able to calculate the probability of H given D using the Bayes rule. You fill up this massive table, one row for every hypothesis. Then you sort the row and the table and take the one that has the highest value. this is what, no matter, this is in some sense what every map learner has to do. In practice, no map learner will do this because our hypothesis spaces are infinite sets, the data sets are massive, it's like just a fruitless exercise. But it's important to keep in mind that in all cases, this is what we demand from any map learner that we have. We are asking that it enumerates every possible function that exists in the hypothesis space, calculate its posterior probability using the Bayes rule, and then find the one that has the highest value. All right, we are at time, so I'll stop. In the next lecture, I'm going to give you 2 examples of maximum likelihood estimation and then go from there. Don't forget your homework, and if don't forget to get started or get going on the project.